Thank you all for coming. My name is Rob Warner. I work at Availity. You see our banners, and you should visit our table and meet Greg Russell. He's the really tall guy. He's a recruiter for us at Availity, and I hope you're enjoying the conference. We're going to talk today about why the web wants WebAssembly. I was feeling embarrassingly alliterative when I wrote my title, and so I was kind of stuck with that, but we have a lot of W's to talk about. There's some contact information. That first link, that repo link, is the repo that contains this presentation and the sample code of what we'll be looking at. So feel free to go look at that and clone it and look at these things. The presentation uses an application called DeckSet, which lets you write the entire thing in Markdown. It's really cool. It's not free, but it's, and I don't get any affiliate links or anything, but you can also just look at the presentation in Markdown, and it's pretty apparent what it does. First of all, how many of you have used WebAssembly? I see a couple hands. How many of you have heard of WebAssembly? I see most hands. There is an explosion of tools available on WebAssembly. I've captured a few links toward the end, but there is so many links now available about WebAssembly, and we'll talk about that and why it's so popular and why it's gaining in popularity. So today we'll talk about what is WebAssembly. We'll look at what are some WebAssembly use cases. How can you leverage WebAssembly in what you're doing? We'll write a WebAssembly application called Adder using the WebAssembly text format. That's the native WebAssembly language. But as we'll find, you can use several different languages to write WebAssembly modules. And we'll also use a language called Rust and a tool called WASMPack to write a WebAssembly module. How many of you have used Rust? Okay, again, not so many hands, but it is a language that is growing in popularity, and we'll talk a little bit about that. Feel free to stop me as you have questions. But according to the WebAssembly webpage, WebAssembly is a binary instruction format for a stack-based virtual machine. So what does that mean? It means it's compiled code, the binary instruction format, for a stack-based virtual machine. So you have a virtual machine that you push data onto the stack, you push operations onto the stack, and the operation operates on the data and pops it off and pushes the result onto the stack. And it's a pretty common paradigm. JVM, CLR, all of these are stack-based virtual machines. So we have the classic example of you have a browser with a built-in WebAssembly host that runs a WebAssembly module. The WebAssembly host being a virtual machine. Now, one of the things that is a little unfortunate with the name WebAssembly is that it's not confined to a browser. As long as you have a WebAssembly host, you can run WebAssembly modules. And there are things like Wasmer that allow you to run WebAssembly from the command line without any browser whatsoever. So we've touched on that it's a binary instruction format, that it's stack-based, that it's hosted. We have to have a host to run it in. And it's also portable. What does that mean? That means that you compile once and it runs on all target platforms. It doesn't matter what the CPU is. It doesn't matter what the OS is. It is a standard binary instruction format, and then the host takes care of things like the operating system and the CPU architecture. So by this time, it should sound a little familiar. What are these? Anybody recognize these? Like who's the guy on the end? That's Java, right? That's Duke from Java. Adobe Air. I see some older people in the crowd. How about that one? Silverlight. Flash. Okay, so these are all technologies that sound very familiar, right? We had a host in the browser, usually a plugin, that ran some sort of binary code that you could run on different architectures and different operating systems. So how is WebAssembly different from all of those? Those have come and either gone or on their way out. Well, one of the things that it's still around, right? These others have peaked, have fallen off. One of the big differences is that it's standards-based. It's a W3C standard. It's not owned by a single vendor. So you have more than just one vendor driving the direction of WebAssembly. And you have the ability for several different companies and several different hobbyists and several different open source developers to build tools around WebAssembly. It supports multiple languages. I include a link on the last page here that has a repository called Awesome Wasm Langs, and you can see all of the different languages that you can use to write WebAssembly modules. You can use Go, you can use Rust, you can use C, you can use C++. It also integrates with the JavaScript. So what does that mean? That means that, let's say you build a page and you have some cool JavaScript stuff going on and some HTML stuff and some CSS, and then you also have some WebAssembly, and those can talk to each other. So this isn't an all or nothing. I once supported a Java applet that ran much of the company's business, and there wasn't that interoperability between the page and the applet. It is sandboxed. So you get the security of the browser sandbox or the host sandbox, and so your WebAssembly module isn't going to overwrite people's file systems or things like that. It's also efficient. As a binary format, it's smaller than a text-based format language. It's also parsed faster, so it downloads faster, it's more quickly parsed, it's a binary format. Questions around that? Browser support. You can see all the modern browsers, the latest browsers, have WebAssembly support baked in. So we have Brave and Chrome and Edge and Firefox and Opera and Safari. There is no support in IE. I keep reading things, making sure that I'm not overlooking something because it should be available in IE. In fact, it talks about how somebody should be able to write a shim for it, but I guess nobody's taken up that challenge unless somebody knows something I don't. But there is a, I guess, sort of reverse compiler that can take your WASM module and compile it to JavaScript, and then you can serve it up for IE. So if you are wanting to hit most sites and then, most users, but still be able to accommodate IE users, that is an option.
Does this include the mobile variant of those browsers?
Yes. Yes, so the mobile browsers as well have that. That's a good question. If you didn't hear, he asked if the mobile variants of these browsers have WebAssembly support, and they do. Okay, so why? Why really do we do this? Well, here are a few case studies that I found. One was eBay. They had a barcode scanner that was in their native app. It was written in C, or C++, I don't remember, sorry. And they had put it on their website and rewritten it in JavaScript, and they were getting 1 frame per second using this barcode scanner in JavaScript. So it was hard for them to get accurate readings. So they took their barcode scanner from their native app, recompiled it as a WebAssembly module, and then they were getting 50 frames per second. So a 50 times speed up. Here's another case study I found. The link is in the end notes about Smashing Magazine. They were able to use WebAssembly to speed up their site 20 times. And then Figma, if any of you use Figma, it's a drawing design application on the web. They were able to cut their load time by 3 times. So here we see some examples of performance gains. However, performance isn't the only reason that you wouldn't just use JavaScript, that you would consider using WebAssembly in your applications. You can look at the performance, but also competition. How many of you remember CoffeeScript? See a few hands. How many of you remember JavaScript before CoffeeScript? And how has the syntax progressed? JavaScript syntax was driven largely by the great syntax of CoffeeScript, and now I don't know if anybody still does CoffeeScript because JavaScript has become so much better of a language. So competition is a good thing. Choice is a good thing. You don't have to just put on your JavaScript goggles to write web applications. Having choice, being able to match skill sets, strengths, the developers you have. Maybe in some scenarios you appreciate type safety and things like that. So when you have choice, you have a better way to address web applications. You can also, like eBay did with their barcode scanner, you can reuse existing libraries. Maybe you have something terrific you've written in C and you don't want to port that to JavaScript. You just want to compile it into a WebAssembly module and reuse that. So what are some use cases for WebAssembly? Why would I use it? What does it do? Well, one of the first things you can do is write your entire application as a WebAssembly module. You take over the entire browser screen, you draw what you draw, you have the controls that you want to have, and you paint the entire screen, you own the browser, your entire application is a WebAssembly module. And we'll see some cases of that. Or perhaps you want to take just a piece of the screen, a frame here, a rectangle there, and write that as a WebAssembly module, paint within that canvas, but then build the rest of your UI traditionally using HTML and JavaScript and CSS. That's also a valid use case for WebAssembly. Finally, you could treat WebAssembly as sort of like a shared library or a DLL that exports functions that you can call. So say you have a function that underperforms in JavaScript, you could rewrite that in a different language, C++ or Rust or whatever, and export that. It doesn't have any visual component. You don't see it on the screen, but your JavaScript can call that function, get the results, and do what it's going to do with that. So those are the main use cases for WebAssembly. Any questions about those? Well, one of the full screen applications that we're going to look at is Google Earth. How many of you have seen Google Earth? So it's experimental, of course, because everything with Google seems to be experimental. They keep that experimental tag on for a long time, but they recompiled Google Earth as a WebAssembly module. So you can see it performs pretty well. It's a little bit jerky, and now you might think, wow, this is magic. It figured out where we are, but this is just a video that I took. But you can see here's a WebAssembly module. It's taken over the whole browser, and you can see Google Earth as a WebAssembly module. Another obvious use for WebAssembly delivered in the browser that takes over the whole screen is games. So for example, Doom 3. How many of you played Doom 3? Okay, so I got to confess, I grew up in the era of the Atari 2600. Anyone? Okay. Have you seen those joysticks? It had one button, one joystick, and I was king. So I thought, well, I'll do a Doom 3 video for these people, and I can't do it. It's too hard. There's like both hands have to go. So we're going to see instead this game called Funky Carts. This is a WebAssembly module. You can play this game, and as far as I can tell, you just need a space bar. So it was exactly my speed, but you can see that you're not constrained in WebAssembly by graphics or anything. There's so much you can do with WebAssembly. Another example we want to look at is the use case of we're going to take just part of the screen and use WebAssembly to render that piece, but then render everything else in HTML and JavaScript. And so I found this application that does some video processing. And it does it in both JavaScript and a WebAssembly module and shows a graph of which is performing better. And I found this goofball to dance for us. But in the top, you can see that's WebAssembly. The bottom was JavaScript. And it's embossing that video from my camera in real time. And you can see how much better the performance was with WebAssembly. So this was a use case that WebAssembly outperformed JavaScript. So that was, we have a piece of the screen that's WebAssembly. We looked at full screen WebAssembly, and now we're going to dig in a little deeper to, we're going to write functions that are exported to JavaScript, and we can call our functions from our JavaScript. Well, what's the first application you usually write when you're learning any technology or programming language? Hello world. Well, we're not going to do that because these are the data types and the only data types supported by WebAssembly. And that, as you probably figured out, is a 32-bit int, a 64-bit int, a 32-bit floating type, and a 64-bit floating type. Now, obviously, we can represent strings and all kinds of data using just those data types, but it's really hard. So that's why the canonical example for WebAssembly is something that either adds 1 to a number you pass to it, or adds 2 numbers together. You pass in 2 numbers and you get the sum. So that's what we're going to write. We're going to write a project called adder, very imaginatively named. It's a WASM function that's going to take 2 integers, and it's going to add those together and return that. We're going to have a little page that has inputs for the 2 numbers and a place to display the sum. We're going to have JavaScript that'll load our WebAssembly module and call our function in response to change events. And then we're going to add some very mediocre styling in CSS. So that's available in that repo from the first slide. So this is the WebAssembly text format. What does it remind you of? What thoughts did you have? Any? A little bit like Clojure, a little Lispish, right? Lispy. A little bit like assembly language, too. So it's kind of this Lispy kind of assembly language. You probably have been able to guess your way through this code, even if you've never seen WebAssembly text. But this is a very simple example. We create a module. WebAssemblies are modules. We create a function called $add that takes 2 parameters, a left-hand side, that's LHS, and a right-hand side, which is RHS. They're both 32-bit integers. And the return, called a result, is also a 32-bit integer. So we're going to push the LHS onto the stack. We're going to push the RHS onto the stack. And then we're going to push the I32 add operation onto the stack. That's going to add those 2 numbers together, pop itself and those numbers off, and pop the result, push the result onto the stack. And then we're going to export that add function as the string add. So that will be visible to callers. And that is our add function. We're going to have some simple HTML that has 2 inputs that are number types, and it has a span for the sum, and it's going to call our JavaScript file that we'll see in a second, whose responsibility it is to load our WebAssembly module and set an event listener. So let's look at this a little deeper. So fetch is your built-in browser fetch in JavaScript. We're going to fetch that compiled WebAssembly module. Then we're going to take the response. Now, WebAssembly is a linear memory model, which means it's essentially a giant array in memory. When I say giant, not so giant really, because you can have those in increments of 64K pages. But we're going to take our loaded WebAssembly module. We're going to use the WebAssembly, which is built into the browser for modern browsers, and call instantiate on that, passing in this array that we've loaded from our WebAssembly module. We're going to take the results from that, and inside results there's going to be an instance called instance that'll be an actual instance of our WebAssembly module. And we're going to pass it into the set event listener. Any questions on that before we look at the set event listener function that we've written? So we've loaded our WebAssembly module, and then we just use standard JavaScript. We're going to go to the DOM and get our left-hand side and right-hand side elements. we're going to create this event listener, and we're going to call WASM, which was our instance we passed in. It exports the add function that we exported from our WebAssembly module, as you'll recall. And we're going to pass in the value of our left-hand side, the value of our right-hand side. We're going to take the results of that call and set it as the text content of our sum span. And then we're just going to add that same listener to both the left-hand side and the right-hand side DOM elements. So if we look at that in action, you can see, there we go. So we go here and we are able to add our numbers together. And so that was our adder application. We were using WebAssembly to add two numbers together. Woohoo! Any questions on that? All right, let's get a little more interesting, because adding numbers together is pretty rudimentary.
Was that WASM that was downloaded, was that just the text format, or was that compiled?
It was compiled. So there's a toolkit, it's called Wabbit. I didn't name it. We wonder why we don't get invited to more parties, but this is this WebAssembly binary toolkit. There's a link to it in the presentation, and it provides a compiler. So we compiled that text format to a WASM module that actually was 41 bytes. So you can see that with the binary format, you can get very small. And with the WebAssembly text format, you can get very small. Good question. Other questions? One in the back.
What was the performance difference on the adder?
The performance distance. Well, I spent about 3 weeks doing performance testing. No, All right, any other questions? One here.
How do you like ignore collisions with the namespace there, where it's like WASM on this point, it's not added?
Oh.
Have more namespace.
Okay, so the question is how do you avoid namespace collisions? Do you mean collisions with JavaScript?
Yeah.
Okay, well, we got to name, this was our results.instance, right? So it's a variable that we are then accepting as WASM. We didn't have to, WASM isn't a keyword.
Gotcha.
We could have called it apples or whatever. And then so we have this variable that points to our WebAssembly module, and then it has an exports, and then it has our exported function. Good question. Back here.
Is there a significant cost crossing the JavaScript to WASM barrier?
There is a cost. Whether it's significant or not will probably depend on the use case, but they are memory safe.
If you want to add 1,000 numbers, or let's say 10 million numbers, is it the cost can be enough where it doesn't make sense to actually use your WASM adder and you should just do the JavaScript?
Yes, absolutely. And my guess, in fact, is that if I had done that performance testing with we're going to performance test our Rust one, but my guess is that JavaScript would have been faster, because you are incurring a cost of calling into the WebAssembly module, and it has to transfer memory safely back and forth. Very good question. Other questions? Okay, so why would we use Rust for WebAssembly? Well, first of all, it is Mozilla backed. I'm not sure if you're aware of that. It was started as a pet project, a side project by someone who at that time was at Mozilla, and it is now backed by Mozilla. It produces very small binaries. Smaller binaries means faster downloading, faster parsing, and so forth. Rust is a very fast language. I'm not sure if you noticed this past week, Microsoft has been releasing some articles about why they're seriously looking at Rust for systems programming. So Rust is very viable in that space. There's great tooling for Rust. How many of you have had to chase, say, C compiler error messages? You get an error message on line 72 and your error was on line 3, and the Rust compiler, for example, provides very helpful messages. There are a lot of great tools around Rust. Some of these languages that are appearing now, if you've worked with Go, for example, all the great tools that come first before they release these things to the public. Rust is also memory safe. Well, what does that mean? It protects you from things like data races, so that at compile time, it catches these potential memory issues and prevents compilation. Rust is a memory-safe language, and the Stack Overflow surveys of the past 3 years, I want to say, it was most loved language. So Rust has a lot going for it, both as a systems language and as a language for WebAssembly. So it's a language worth looking into. I put together this little chart to get you started if you haven't used Rust, but you are familiar with JavaScript. How many are familiar with JavaScript? I would think a lot of people here. So NPM or Yarn or, and I keep forgetting the name of that new one. What's that? Maybe, I don't know. Somebody that was on the NPM team that broke away. But anyway, with Rust, you have Cargo. Cargo is the tool you use to create projects, to add dependencies, everything, the same sorts of things that you use NPM for, you use Cargo for. Your package.json that contains metadata about your project, contains your dependencies and so forth. You have cargo.toml in the Rust world. And your node modules, you have crates. Third-party libraries are called crates. So that is your primer on Rust, and now you're all Rust developers. There you go. There we go, crustaceans. And that's a reference to I guess it's the mascot for Rust is this crab. Here's a couple of tools that make developing Rust WebAssembly modules and using those in JavaScript very easy. We're going to look at WasmPack. Neon is another tool. I see the guy that pointed me out to it in there in the back. Say hi, Rob. But these tools, what they do is they allow you to write libraries in Rust, compile them as WebAssembly, and then use those as node modules. You can post them to NPM, publish those, and use those transparently as node modules. So we're going to build an application called Colors. In this application, we have one input field. It's a color input field up at the top. Allows the user to select a new color, and it will instantly compute, or at least as fast as the language will allow, will compute the triadic, which is that color, the color 120 degrees through the color wheel, and the